Let's do a little bit more about formal charges. And again, as we said before, we need to know our valence electrons, and I'm going to draw my little periodic table that we use in organic chemistry. So here we go, hydrogen, and then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and here's neon, helium, and as I said, we use also chlorine, bromine, for example, right below. Oxygen is sulfur. Here we have phosphorus. And most organic chemistry, we're going to be using this part. And of course, hydrogen. So that is. And how do we know about our valence electrons? We remember this is group 1. So 1 valence electrons, 2, 3, 4, 5, 6, 7. And here will be 8, right? So these numbers, the group numbers tell me the number of valence electrons. And as we said before, for formal charge of an atom, say X, we are going to then look at what is the number of valence electrons, and we're going to subtract the number of electrons in bonds and divided by 2, because here we're considering electrons in bonds equally shared by the 2 atoms. And then we add here the electrons in lone pairs. Right, so it came out a little inclined. All right, so that's what we're using. And simply what I'm going to do now is apply that formula to some molecules. So say that I have now this structure. So here I need to determine, so formal charge of carbon. And now I know group 4 is 4 valence electrons minus, and I'm going to count the number of electrons in bonds, 2, 4, 6, divided by 2, and then the electrons in lone pairs, so 1, 2. So, and here it is, 3 and 2 is 5, so that charge is -1. So -1 here. That is a carbanion. So now what if I had just this and no lone pair? If I don't have a lone pair, again, using my formula, I'm going to say formal charge of carbon. Number of valence electrons is still 4. It's the same. It's for carbon, right? Then minus the number of electrons in bonds divided by 2. So 2, 4, 6 divided by 2. And I don't have any electrons in lone pairs, so that is a 0. And that gives me a +1 charge. So this right here is +1. This is a carbocation. This is a carbanion. Okay, so we're going to do one more. Say here, applying the same formula. Now, let's say that I have, we're starting from a Lewis structure. 1, 2, 3. That. By the way, if we analyze that Lewis structure, it's good in the sense that we have all the electrons, and here octet is complete, 2, 4, 6, 8. Same thing for the oxygen. But now let's see if we have or not formal charges. And for that, we're doing a quick check here. So that is easier for us later when we see more complex molecules, I'm going to do methane. And so notice that here I have missing 1 hydrogen, and here I have 1 lone pair. This is with the 4 hydrogen, and here the formal charge of carbon is 4 valence electrons minus, and then 2, 4, 6, 8 divided by 2, 0 electrons in lone pairs, so that is 0 formal charge. What that says is that a carbon with 4 bonds and no lone pairs has a 0 formal charge. So right here, I know that this carbon has 0 formal charge, has the same bonding pattern that we have here in methane. So we're going to calculate the formal charge in this carbon and in the oxygen. So let's say formal charge of the carbon, but this, okay, the one on top. So now, again, we start from valence electrons. We have 4 minus the number of electrons in bonds. So 2, 4, 6, 8, right? And that is divided by 2. And no electrons in lone pairs. So same pattern. That will be 0 formal charge. What happens to the oxygen now? And so let's delete, remove this formula right from here. Because I need a little bit of that room. And so I'm going to do the formal charge for the oxygen. Formal charge of the oxygen. Next, we need to check our valence electrons. 1, 2, 3, 4, 5, 6, right? It is in group 6 minus the number of electrons in bonds to oxygen. So let's say 2, 4, and 6. Divided by 2, and then I have 2 electrons in lone pairs. So 2 here. So what do we have here? This is a total, that'll be 3, and 2, that's 5. So what is the formal charge here? Is plus 1. So another thing I want you to notice is bonding patterns. So when we have, again, a carbon atom with 4 bonds in no-lone pairs, that pattern is 0 formal charge. And let's do patterns for oxygen. Let's do, for example, water. And ethers are similar, just replacing the H's by R groups. But what is the formal charge here of oxygen? It would be 6 valence electrons minus, and then bonds here, electrons and bonds. So 2 and 4 divided by 2 in 2, 4 electrons in lone pairs. So that right here is 6, so formal charge is 0. So bonding pattern of oxygen with 2 bonds in 2 lone pairs is 0 formal charge. A bonding pattern of oxygen with 3 bonds, say hydronium ion. Hydronium ion is this. Now, if I do hydronium ion, 6 valence electrons minus 2, 4, 6 divided by 2 in 1 lone pair here. So 1, 2, right? And so that bonding pattern give me a plus 1 formal charge. So similar to that. Again, pattern is an oxygen with 3 bonds and only 1 lone pair will have a plus 1 positive charge. So it is useful to learn bonding patterns, and we can assign faster the formal charges.